All right, welcome back. Chapter 8.1, accumulation and area under a curve is basically what this section was about, applications of integrals. So what do we need to know? We need to know that the total of anything is equal to the area under the graph. And the tricky part is just the relationship between the graph and the total of what it is you're trying to find. So usually in a problem like this, what we've got is we have a graph that represents some kind of rate versus time. We've got some equation and the accumulation of whatever is accumulating at that rate, integral slash area under graph. So really the big idea is to do this analysis, and what we want to do when we analyze is we want to figure out what is the rate, and therefore what is accumulating. If it is a rate of snowfall, then snow is accumulating. If it is a rate of speed, then distance is accumulating. If it's a rate of acceleration, then velocity is accumulating. And you can think back to all the examples we've done over the course of this section. If it is a rate of force, work was accumulating. You could just go back and just look at every one of those examples. A rate of density, then amounts are accumulating, since density is how many of something per square mile or per yard or whatever it is, per square yard, whatever that is. So what's the trick to finding these things? Well, first off, figure out what your Riemann sum is. You're going to have some Riemann sum that's a function. You're drawing yourself a little diagram and saying, well, there's my rectangle, and this is f of x sub I, and this is delta x. We'll assume constant delta x on these because it doesn't matter, because when you do that, you can then convert this into an integral f of x dx from a to b. This is going to be the tricky part right here, is what is that Riemann sum? And the problems I'd recommend you go back and look at as far as non-straightforward are going to be the work problem that we did in the last video and the density problem of gophers in the previous video. And you'll see where it's so important to draw yourself those little sketches and see if you can figure out, okay, how do I figure out what it is I'm trying to find using that sketch. All right, so let's just do a quick recap of the examples we did. We had work was the area under a force curve. We had gophers was the area under a, and now be careful here, 10 times the density of the gophers curve because of the width of the problem, the length of the strip. We had gallons, which was the integral of the rate of pumping, area under the rate curve. We had population, and this was the amusement park problem. Whoops, population. And remember, you had some initial population. You were adding how many people had entered, which is the area under the entering curve, and you were subtracting how many people had left, which was the area under the leaving curve. You had cumulative consumption, which again, cumulative consumption, which again, cumulative consumption is like an accumulation, except I'm using it instead of stacking it up. Integral of my consumption curve as a function of time. In other words, a rate of consumption. And then, of course, we had distance traveled. And we have to remember that it's the absolute area under the velocity curve versus displacement, how far I have gone, displacement, which is just area under the velocity curve. Of course, when I'm going backwards, my displacement integral will then be negative, and my displacement is changing backwards, whereas distance traveled, when I'm going, doesn't matter what direction I'm going, so everything becomes a positive. All right, I think that those are the examples we did here. And if you see a problem that's asking for some kind of accumulation, it's just a function of translating it in your head and saying, this is an accumulation. What do I know about the accumulation? Can I build that Riemann sum? And then can I convert the Riemann sum to an integral? All right, thanks for watching. I hope you learned something.